Hello, I'm Professor D, and I'm back to take another in-depth look at Calculus 2. In this case, we're looking at applications of integration. In section 2.4, we're looking at two applications of integration. Arc length of a curve, as in a plane curve, how long is it? And that's difficult to find if it's curved, of course. And the second application is going to be surface area of a volume of revolution. Now we've just completed talking about volumes of revolution, but we haven't talked about how much paint it would take to paint the outside surface of that volume of revolution, or to cover it with wrapping paper with no overlap. That's what we're talking about when we're talking about surface area of a volume of revolution. In this first video, we're going to focus on arc length, and in the next video, we'll focus on surface area. Let's get started. What we're looking at right now, of course, is arc length of a function of x. Now, the curve is a function of x. We'll also look at some that are maybe a function of y. But in the first case, what we want to know how to do is how to find how long it is. So we study arc length also in the parametric coordinate system and in the polar coordinate system. We're going to have to make some requirements on the kinds of functions we study in order to make it possible to find the arc length of a curve. In particular, what we're looking for here is what's called a smooth graph. Now, smooth is what you think it would be, no pointy parts, basically. It also implies that it's continuous. So it's got to be continuous, it has to be differentiable, and even stronger, the derivative function itself has to be continuous. That's what it means for a curve to be smooth. All right, so when we look at the definition of smooth down here, what we're basically saying is because it is continuous, then there are no places where we've got vertical asymptotes, holes, jumps, or those kinds of points, all right? So we basically have no breaks in the graph because it is continuous. Now, because it is differentiable, we know we have no places of vertical tangency. We also have no corners and no cusps. Now, because the derivative function itself is also continuous, that means the derivative function also must not have any holes, no displaced points, no jumps, no infinite asymptotes, vertical asymptotes in the graph of the derivative function. If we have these conditions, the function is continuous, it has a derivative, and the derivative function is also continuous, then we can say it's smooth. And if it's smooth, what we're going to be able to do is we're going to be able to take a curve, and you can see the curve here in dark blue, and we're going to be able to divide up the region between x equal a and x equal b into partitions. You know, this is the calculus thing to do, right? We chop stuff up, we add them together, take the limit as the number of partitions goes to infinity, and we get a definite integral. So when we're looking at this, what we want to do is we want to divide the region over which we want to find the length of the curve, the blue curve, the smoothly curving function. And what we're going to do is we're going to approximate the length of each little curved part with a straight line segment. So we're going to take the two endpoints of each partition and we're going to connect them with a straight line. And we're going to approximate this curved piece with the length of this straight line. Now, as we increase the number of partitions, the width of each partition gets smaller and smaller. And because we've required the function to be smooth, that means that as these become narrower and narrower intervals, these curved sections will become more and more linear. And that means that the approximation using the straight line segment gets closer and closer to the true value of the curved section. Now, how are we going to approximate that line segment that we've got right there? Well, obviously, we're going to use the Pythagorean theorem. So what we're going to do is we're going to look at this graph right here, and we're going to use the Pythagorean theorem to find the length of that orange, red, line segment, and then we're going to use the Pythagorean theorem to find the length of that orange-red line segment, and then that one, and then that one, and then that one. We're going to add them together, and then we're going to take the limit as the number of partitions goes to infinity, or saying the same thing, delta x goes to 0. And that will give us the true value of the length of the blue curve from x equal a to x equal b. Let's now look at how we find or how we use the Pythagorean theorem. So you can see right here, I have a close-up of 2 points that are on the particular curve. And these are at the very beginning. So this is x naught, which is actually a. So this point right here is actually a f of a, or you could call it x naught f of x naught. And this point right here is x1, the end of the first partition. And so this would be the point x1 f of x1. And we want to find the length of this orange-red line segment. To do that, we're going to create a right triangle. So we drop a vertical straight down and we create a horizontal to create a right triangle right here. And when we're looking at this right triangle, of course, we've got the mark right there in the corner. It is a right triangle. And notice that this vertical measure is the change in the y value between f of x sub I minus 1 and f of x sub I. Or on this particular one, it's f of x1 minus f of x naught. That's the change in the y values. The change in the x values is just going to be given by x1 minus x naught. And over here, it would be given by x sub I minus x sub I minus 1. Now, we tend to always want to do regular partitions, and that means all our delta x's are the same length. That's actually not required by the proof. All the proof requires is that the widest one, which is called the mesh, does go to 0 as we take the limit. So they could all be different widths. It'll still work as long as even the widest of all of the subintervals goes to 0 when we take the limit. And then, of course, we can use the Pythagorean theorem. So the length c of this hypotenuse that we've got here, which is, of course, the approximation that we're using for our curved region in dark blue up here, c becomes the square root of delta x squared plus delta y squared, where this is delta x sub I, the width of the ith interval, and delta y sub I, the change in the y value on the ith interval. Let's take a look at what this looks like on a real curve. So we've got a curve right here, and you can see that this one is, it's very smooth. It's smoothly arced. It is continuous. It is differentiable. We can't prove it without the function, but the derivative function is also differentiable. And you can see that we have orange-red line segments connecting each of the subintervals. They're very, very close to the actual curve, which makes them a really good approximation. And again, we have the change in the x values given by x sub k minus x sub k minus 1. And we have the change in the y value for the kth interval, which would be delta y sub k. And of course, we can use the Pythagorean theorem to find the length of that orange-red line segment, which is going to approximate the length of the curved function, which is in this, I think, black, if I'm looking at it right. Now, one other thing that you might want to notice here is that we actually have a secant line. So what we're using right here is actually the secant line across this subinterval. That's the line that cuts through. And the slope of this line right here would be delta y sub I divided by delta x. Now, from now on, we're going to assume that we're using a regular partition. That will make it a little bit easier for us. But again, the slope of this line right here is delta y sub I divided by delta x. Now, you may go, why is she talking about the slope of the secant line? Think back, what theorem do you know says something about the slope of the secant line compared to the slope of a tangent line at a particular point? Yes, I'm foreshadowing. We're going to be using the mean value theorem. Before we get there, we need to do some algebraic manipulation in order to get that slope of the secant line into our formula. Right now, our formula for the hypotenuse is delta x sub I squared plus delta y sub I squared, all under the square root. It's just the Pythagorean theorem. And that gives us lowercase l, which is the length of the hypotenuse of the right triangle on the ith subinterval. We want to get delta y sub I divided by delta x into this equation because, of course, delta y sub I divided by delta x is a secant line. And with the mean value theorem, I can show that it's equivalent to the derivative at some value c in that interval. So we're going to do an algebraic manipulation here. We're going to actually multiply by delta x divided by delta x, which of course is just 1. So I'm allowed to do it anytime, anywhere, much or as little as I feel like it. So I take the Pythagorean theorem. I multiply by 1 in the form of delta x over delta x. I'm going to leave the numerator factor outside the radical, but I'm going to move the denominator factor underneath the radical. Now, to move it under a square root, I have to square it. So I square the delta x and move it underneath the radical. Now it's still multiplied by delta x quantity squared plus delta y sub I quantity squared, those added together. So then I go ahead and distribute. So I get delta x quantity squared over itself, which of course reduces to 1. And I get delta y sub I quantity squared over delta x quantity squared. Now this is very close to what I wanted, which is the slope of that secant line, because I want to use the mean value theorem. So then I just pull the square out of each one and put it on the whole thing. And here is the slope of the secant line coming right here. So this expression that you see right here is the slope of the secant line. Oops, my pen's not writing. Slope of secant line on the ith subinterval. So now what do I do? Well, now I'm going to invoke the mean value theorem. Now, again, what are the conditions of the mean value theorem? It must be continuous over the open or closed and differentiable over the open. But we have that because we required something even stronger. We required it to be smooth. It has to be continuous, has to have a first derivative, and the first derivative has to be continuous. That's not required by the mean value theorem, but we're requiring it to make it smooth. We need that later on in order to prove something else. So now what we have is we can apply this mean value theorem because it meets the conditions. And we know there has to be some x sub I star, or you could call it c sub I, whatever you want to call it, in each subinterval. So somewhere between x sub I minus 1 and x sub I, there's a special x value. And at that special x value, the slope of the tangent line at that point is equal to the slope of the secant line. Now, the secant line, of course, is this orange-red hypotenuse here. And now we need to find that other point. So I'm kind of guesstimating here, but that looks roughly parallel, doesn't it? So the slope of this line has to be the same as the slope of that line. And this is guaranteed by the mean value theorem, which means this point right here, coming all the way down, this must be my x sub I star, all right? So I've got x sub I star at this point right here. Now, why do I need that? Well, this allows me to replace the slope of the secant line with the slope of the tangent line at a particular point. Remember, the differential delta y is not the same as the differential dy. I want to get rid of the delta y so that I can do something that I can integrate. And I've got to get out of this delta y and get to a dy. And the first derivative does that. That is basically dy dx evaluated at x sub I star. So now let's take a look at what we've done to the equation. We've now changed our approximation. We still have the numerator delta x factor on the outside. We've changed the slope of the secant line into the slope of the tangent line at that special spot inside each subinterval. Now what we want to do is, of course, we want to add together this approximation for all of the hypotenuse in our subintervals. So we're going to take all the little L sub i's, all these approximations using the Pythagorean theorem to get an approximation of the length of the entire arc from x equal a to x equal b. And we call that uppercase L, which is the sum of all the little L sub i's. Now, remember from what we learned in the linear approximations section in Calculus 1, that the differential dx is always, in fact, delta x, that they are, in fact, the same. But it is delta y and dy that are not the same. Dy is on the linear approximation function, also known as the tangent line, and delta y is the actual change in function values on the function. So we're able to replace the delta x with dx without any loss of information. And so now what we're going to do is add all of these together, and then we're going to take the limit of the Riemann sum. And this is what we have. The arc length is approximately equal to the sum from I equal 1 to n subintervals of the Pythagorean theorem times delta x. Delta x becomes dx. And over here, we're going to take the limit as n goes to infinity, which is the same thing as saying delta x goes to 0, same thing. And this leads to the definite integral from a to b of f prime of x quantity squared plus 1 under the radical with a differential of dx. And again, we needed smooth in order to prove that this value right here does approach f prime of x as the width of each subinterval goes to 0. So here's our formula. If f of x is a smooth function, continuous, has a first derivative, and the first derivative is also continuous, over the interval closed a to b. We have to apply the mean value theorem, so this has to apply on the closed interval. Then the arc length of the section of the graph from a f of a to the point b f of b is given by this definite integral. Now what we want to do is we want to go ahead and take a look at some examples. All right, so let's go ahead and dive in and take a look at our examples now. In example 1, we have the following problem. F of x equals 4/3 x to the 3/2. Now, this looks more or less like the right arm of an upward opening parabola. It's not, but it's similar to that graph. Notice it doesn't have a left arm because the 1/2 power represents square root, so you can't put a negative underneath there. So this is basically what the graph looks like. I've only graphed a small section of it. And we want to find the arc length, how long this curve is over the interval from 0 to 1. So this is x equals 0 to x equal 1. And in the graph down here, I've shaded the section I'm interested in measuring the length of in blue. So we want to round our answer to 3 decimal places, and I have the function right up there. So the first thing we need to do is find the derivative. So we're going to find the derivative by taking the derivative of our function, finding my place in my notes. So step 1, find f prime of x, which is going to be equal to, we'll bring the 3/2 to the front, multiplied by the 4/3 that was there, reduce the power from 3/2 to 1/2. Now the 4 divided by 2 is 2, the 3's cancel, and the 1/2 power is the square root. So I get 2 square root of x. That's step 1. It's usually easier to go ahead and figure out what the radicand is, what goes under the radical, before you write the integral. Otherwise, you're doing a lot of rewriting that's not necessary. Step 2, find the derivative quantity squared. So now we're going to take the derivative, 2 square root of x, and we're going to square it. And this gives us 4x. Step 3, add 1 to it. So now I have 4x plus 1, or 1 plus 4x, whichever way you want to write it. It is commutative. They're both positive. So now I know what I need to put underneath the radical. I know that I'm interested in the region between x equals 0 to x equals 1. So I have the values of a and b. So I'm all set. So go ahead and pause the video here, work out the integral, then turn the video back on, and let's compare our answers. So I've shared my screen with you so you can more easily see the work that I've done. So I wrote the integral from 0 to 1 of the square root of 4x plus 1. I did a u substitution over here, changed the limits of integration from x values to u values, so I don't have to go backwards to x. It's usually less work, although students tend to prefer not to do it. Don't ask me why, it's more efficient. So when you get this, you end up with u to the 1/2 times du over 4. And then when you integrate u to the 1/2, you add 1 to the power. So you get 3/2, divide by 3/2, which is multiplied by 2/3. And when you work out the arithmetic and algebra, you end up with 1/6, the quantity 5 square roots of 5 minus 1. That's the exact value. And it's approximately 1.697, or about very close to 1.7. So let's come back to our graph and see if we buy that. If we're looking at this right here, I know that this length from here to here is 1, and this length right here is definitely longer than that. It does look like it could be about 1.7 long, so my answer seems reasonable. All right, let's take a look at the next example, which is example number 2. In example number 2, we have the function x squared minus 2, which of course is an upward opening parabola, then shifted down 2, so the vertex is down here at 0, -2. And we want to calculate the arc length over the interval x equal -2 to x equal 3. Here's our formula again. So go ahead and pause the video, try this one on your own, then turn the video back on and we'll compare our answers. Remember, find the derivative first, then square the derivative, then add 1 to that. So this is a really difficult problem. If you've already given up and thrown your hands in the air, it'll be a good review for you of integration techniques. So let's take a look and see what we've got going on here. If we're looking at this integral, so we took the derivative and got 2x, which is pretty simple, squared it to get 4x squared, add 1. You have the radical of 4x squared plus 1. This is a trig substitution problem. So remember, you take the square root of the variable term, which is going to give us 2x. And because it's a plus, it's going to be tangent. So we have 2x equal to tangent of theta. And it's going to be 1 tangent of theta because that was a 1 right there. Now we try to recreate what was under the radical. So we find 4x squared plus 1. So we square the 2x, which is tangent. And that gives us tangent squared of theta. Then we add 1 to get tangent squared of theta plus 1. Now that is the Pythagorean identity for secant squared. So the next thing we have to do is we're going to replace what's under the radical with secant squared of theta. But that means that our differential is switched from dx to d theta. So I got to find that. So what I need to do is write an expression for x and take the derivative. So I take my original substitution equation, 2x equal 1 tangent of theta, divide by 2 to get x's half tangent of theta. Then I'm going to take the derivative with respect to theta. When I take the derivative with respect to theta, the next thing that I'm going to end up with is dx d theta is 1/2 secant squared of theta. And then we abuse the notation and slide the d theta around. So I'm going to replace the differential dx with 1/2 secant squared of theta d theta. Now remember, when you have cosine or secant, you don't have to worry about taking the square root of something squared. It's always going to be strictly positive. The only one you have to worry about is the one where you end up with tangent underneath the radical. That one you do need to worry about the signs. So we go ahead and make the substitution. We put secant squared under the radical to replace 4x squared plus 1. We replace dx with 1/2 secant squared of theta d theta. And when we take the square root of secant of theta, we get absolute value, but in this case, it becomes just secant of theta. And then we multiply it to get 1/2 secant cubed of theta. Now, you may have gotten that far, but then you probably threw up your hands because you're like, oh my God, I don't remember how to do this. Integration by parts. So we'll go through it relatively quickly. We let u be one of the secants because we need secant squared to be dv. So we want secant squared to be dv because we know how to integrate that. It becomes tangent of theta. We choose the constant to be 0 in integration by parts. And then we say that the integral of 1/2 secant cubed of theta d theta from x equal -2 to x equal 3 becomes uv minus the integral of v du. When we substitute each of those parts into our integral, we end up with 1/2 secant theta tangent theta, again from x equal -2 to x equal 3. I chose not to replace the limits of integration because I think the trig substitution with the integration by parts makes it hard enough. I thought it would be better to go back to x. And then over here, for our v du, we get 1/2 secant of theta tangent squared of theta d theta. This is a trig integral. I know, it's like I've thrown the entire toolbox of integration techniques into the same problem. I did, pretty much. So what we're going to do is, because that's an even power of tangent, we want to get to all secants. So we're going to replace tangent squared with the Pythagorean identity secant squared minus 1. So when we replace that and multiply it out, we get 1/2 secant cubed of theta minus 1/2 secant of theta. So now we've got this part right here. And it's kind of hard for me to get it all on there at the same time. So this is from our uv, which is just tagging along. And then we split this part into 2 because we replaced it with the Pythagorean identity. Now, a lot of students at this point get a little lost and they're like, I don't know where to go from here. But remember that this was the original. And what you have down here is not exactly the same, but it's certainly a like integral. They're both 1/2 secant cubed of theta d thetas. This one's a positive 1/2. This is a negative 1/2. So you're going to move this one to the left side of the equation by adding it. Now, L is equal to 1/2 secant cubed of theta. And when I move that one, I'm going to get 1 secant cubed of theta, which isn't going to be L anymore. It's going to be twice L, right? Because L is equal to 1/2, when I get the full 1, it becomes 2L. So you can see right here, I've got 2L. And then the next thing that I'm going to have, so I've got 2L right here. And then I've got secant cubed of theta d theta. Here's uv again. And here's the one term that got left after being split off from the Pythagorean identity. Now, this is another one of those ones you should know. There's a trick. You multiply by secant theta plus tangent theta divided by itself. It gives you 1/u du, which results in the natural log of the absolute value of u, which is secant theta plus tangent of theta. So now we need to go ahead and figure out these values. So now this is not giving us the arc length, it's giving us twice the arc length. The arc length is half of this integral, but that's okay, we can keep working with it. So what we're going to do now is we're going to go back to our original substitution equation, which was 2x equals tangent of theta, draw the triangle. Tangent, of course, would be opposite over adjacent. So this is 2x and this is 1. The Pythagorean identity then gives us the hypotenuse as radical 4x squared plus 1. If this is not what you had in the original, you've made a mistake. It should be, and it is. Now I can take the triangle and I can look up here. I know what tangent of theta is. It's 2x. So I can replace the tangent of thetas with 2x, but I need to replace secant of theta as well. And looking at the triangle, secant is going to be hypotenuse over adjacent. So secant of theta is the radical 4x squared plus 1. Now I'm going to make that substitution in the next line. So it's kind of difficult to get all this on one screen. So I've still got twice the arc length, and I've got 1/2 secant theta tangent theta. So here's secant theta, here's tangent theta. I can drop the x equal because now the limits of integration match the variable in the problem. Before that, I had to write them because they didn't match. And then over here, I've replaced secant of theta with radical and tangent of theta with 2x. And then, of course, it's just a matter of plugging in and simplifying. And when you're done, you end up with an expression that looks something like this. It can be simplified a little bit further, but remember, this is 2L. When we added that integral to the other side, it doubled the integral. Instead of being 1/2 secant cubed, it became 1 secant cubed, which is twice what we needed. So this is still 2L. So to find L, I'm just going to divide everything by 2. And this gives us our final result, which you'll see down here, 3/2 root 37 plus square root 17 plus 1/4 the natural log of root 37 plus 6, all divided by root 17 minus 4. And again, this is actually strictly positive, so you can drop the absolute values. And I use that algebra rule where when you're subtracting and the bases are the same, you can write it as the ratio of the two values. And this turns out to be about 14.394 or about 14.4. So let's go back to our original picture up here. And let's look at this curved length from here around to here, keeping in mind that this distance right here is representing 1 or 5 rather. So if this distance is 5, do we buy that this amount right here is about 14.4? Yeah, it looks like it's about 3 times that distance. So it's very close to 15. So yeah, I'll buy it. All right. Seems like a reasonable answer. A very difficult problem, but a reasonable answer. Let's now move on to the next example, which is going to be example 3. Now, that is the hardest one in the set, so no panicking. It's definitely the hardest one in the set, so you don't have to worry about there's going to be a worse one coming up. There's not. All right, so let's take a look at example 3. Now, I like to give problems like example 3 on my exams because they're doable in a reasonable amount of time. The previous problem is not reasonable. It's a great homework problem because it makes you review all your techniques of integration, but it's a terrible exam problem. But this is not. This is a great exam problem, but it is tricky. So make sure that you're paying attention because there is a weird little thing that happens here with a minus 1/2 becoming a plus 1/2 that allows us to refactor it into something that is basically like a binomial square. And that will let us get rid of the radical. Okay, so we're going to start the same way that we always start. We'll go ahead and work through this one together. So when we're looking at this one, the first thing we want to do, of course, is find f prime, which is going to be 4x to the third over 4. And in order to take the derivative of this, it might actually be easier to write it in a slightly different form. This could be 1/8 x to the negative 2. And then that way you can just apply the power rule because really who wants to do the quotient rule? I avoid it like the plague when I can. So this becomes a minus 2 over 8x to the negative 3, which is going to give me basically x cubed minus 1/4, and then the x to the negative 3 drops to the denominator, and I get 1 over 4x cubed. All right, so this is our first derivative. And after taking the first derivative, the next thing we want to do is we want to square that value. Now this you cannot mess up. If you mess this up, you just tank the whole problem. So you're going to have to get your algebra skills on. So part 2, find the first derivative and square it. So this, I'm going to go ahead and write out twice so that we can actually see it. I've found over the years that writing it out actually saves time in the end because the brain only can hold a certain number of items in there at any one time in working memory. I don't remember what the number is, but it's low, right? Like 5 or less. So it's low. So if you're making the brain remember what these are, it decreases the efficiency of the brain, and that's why you make mistakes. So better to write it out so you can see them, and then you don't have to keep them in your head. You can just multiply them together. So this is going to give me x cubed times x cubed, which is going to give me x to the 6th. Add the powers when you multiply bases that are the same. On the outside, I get a minus x cubed over 4x cubed. And on the inside, I get the same thing. Again, that's 2 of them. That's because this is like a binomial square where you double the outer and inner product when you combine them. And then the last times the last gives me a plus 1 over 16x to the 6th. Now, the x cubes are going to cancel in this part here, and I get minus 1/4 and minus 1/4, which gives me a minus 1/2. That minus 1/2 is key. If you don't get it, you've already got an error. Go back and check. So now what I've got is x to the 6th minus 1/2 plus 1 over 16x to the 6th. Now, why is that so key? What difference does it make? Well, it makes a huge difference, because whatever we get after we add 1, we're going to have to put under a radical. And in order to be able to integrate it, it'd be nice to be able to get rid of the radical. So I want something that's squared to go under there. And it turns out that because this is a minus 1/2, and step 3 is to add 1 to it, when you add 1 to a negative 1/2, it becomes a plus 1/2. So let's write that down as our next step. So step 3, add 1. So this is going to give us x to the 6th plus 1/2 plus 1 over 16x to the 6th. And you may look at that and go, that does not help me at all. That's going to be a nightmare trying to put under that radical. How am I possibly going to do it? These are identical, except for the sign in the middle, which means this one has to factor the same way this one did, but instead of a minus in the middle, it has a plus. In other words, these are the same pattern for something squared, but this one has a plus in the middle and this has a minus, which means that this has to become x cubed plus 1 over 4x cubed times x cubed plus 1 over 4x cubed. In other words, it factors exactly the same, but with a plus instead of the minus. Now we want that because this, of course, is squared. This gives us x cubed plus 1 over 4x cubed squared. And now when I put it under the radical, I'll be able to take the square root of it. It'll give me absolute value. I'll have to worry about that, but it's not going to be too bad. So we're going over the interval from 1 to 3. It's kind of an interesting graph. It kind of reminds me of a curvy W, capital letter W, except that it's got a vertical asymptote here, of course, at x equal 0. And we're only looking from 1 to 3. We cannot have that discontinuity in our interval. Remember, it's got to be smooth, continuous. It's got to have a first derivative, and the first derivative has to be continuous. First derivative doesn't exist if the function doesn't exist. It's not continuous there. So ours is going to be from 1 to 3, which is this blue section right here. And we're trying to estimate how long that is. So just offhand, since from here to here is 20, I'm going to go with 24, 25. I don't know, something like that. All right, so now we're going to put it under our radical. And we're going to integrate from 1 to 3. And we have the square root of x cubed plus 1 over 4x cubed. Now, we should be worried about taking the square root of something that's being squared. So we need to think about that. This is going to give us absolute values when we take it out. But where are my x values? My x values go from 1 to 3. In other words, they're always positive. And if they're always positive, then this is always positive. So I can drop the absolute values. I'm also going to rewrite 1 over 4x cubed in a form that's easier to integrate. So I get 1 to 3, and this is going to be x cubed plus 1/4 x to the negative 3 dx. And now I can simply apply the power rule. So go ahead and pause the video here and take a moment to go ahead and figure out what it is, then turn the video back on and we'll compare. So let's take a look and see what you got. So we put this underneath here. We're going to take the square root of the square, which gives us absolute values. Again, the absolute values were between 1 and 3. So they're always strictly positive. So we can drop the absolute values. This gives us this. And then, of course, after integrating, we come up with this, which simplifies to this. And then when we plug in the limits of integration, we get 181 over 9, which is 20.1 repeating. So I was a little off on my estimate. I thought it was around 24, 25, but I'm close. I'm ballparking it. My eye's not that great at judging distance, so that's pretty good for me. All right, let's take a look at another example, and then we're going to switch to doing arc length with respect to y. So now we're going to take a look at this one right here. This is example number 4. Let f of x equal the natural log of the sine of x, which is really a kind of a fascinating curve that we've got going on here. It looks more or less like a higher even degree polynomial, something like an x to the 12th or something like that, where it's real flat in here, but opening down, so like a negative x to the 12th. But it's been shifted over to pi over 2, where this pot is really close here. We're interested in this section right here, where x is between pi over 6 and pi over 3. So we're going to calculate the arc length using the methods that we've done previously. So let's go ahead and find f prime first. So that's step 1, find f prime, which is going to be equal to, well, the derivative of natural log is 1 over u, so we get 1 over sine, times the derivative of u, which is cosine. And the derivative of x is just 1, so that doesn't change it. So this is really cotangent of x. And then step 2, we're going to find that squared, which is going to give me cotangent squared of x. And step 3, we add 1, which is going to give me cotangent squared of x plus 1. Now, you should recognize that. That's a Pythagorean identity. This actually becomes cosecant squared of x. If you don't see it, you're going to have a really difficult time integrating, because we need this single term factor here to be under the radical so that we can take the square root of it. And again, in this case, cosecant, we're not worried about whether or not it is positive or negative when we take it out, because we know that cosecant is strictly positive over this range of values. These are both in quadrant 1, and everything is positive in quadrant 1. So let's go ahead and complete this work. So we have L equal to the integral from, let me see, what was it? Pi over 6 to pi over 3. And I will take care to write it out exactly so you can see why it becomes what it becomes, which becomes the integral from pi over 6 to pi over 3. And again, we originally get absolute values, but cosecant of x is positive in quadrant 1. So it's definitely positive over pi over 6 to pi over 3. So this becomes the integral from pi over 6 to pi over 3. Oops, and I don't have a square anymore. I lost that. So this becomes cosecant of x dx. That's what happens when you try to write fast. All right, now this one, there is a trick, which is, of course, multiplied by cosecant plus cotangent divided by itself. So I will write out the steps of that, but in case you have it memorized, you can go ahead and do that as well. So this is pi over 6 to pi over 3. and we have cosecant of x, and then we multiply by cosecant x plus cotangent of x divided by itself. And this actually ends up with 1 over u du with a negative thrown inside. So writing this over to the side, du becomes the denominator, cosecant of x plus cotangent of x, and du becomes, oops, not d, u becomes that, du becomes negative cosecant cotangent minus cosecant squared of x. And then all of this times the differential dx, which is the opposite of what we would end up with in the numerator. This would give me cosecant squared, and this would give me cosecant plus cotangent, but these would all be positive. So I've got a negative in here. So it becomes a negative du. So now when I integrate this, I'm going to end up with the following, and I'm not going to switch this time my limits of integration. So I'm going to basically end up with x equal pi over 6 to x equal pi over 3. And I'm going to have u, 1 over u, times a negative du. And this is going to give me negative the natural log of the absolute value of u, evaluated between x equal pi over 6 and x equal pi over 3. And then we can go back to what our u was, which was negative natural log of the absolute value of cosecant of x plus cotangent of x, evaluated from pi over 6 to pi over 3. So let's go ahead and figure out what that turns out to be. The cosecant of pi over 6, well, sine of pi over 6 is 1/2, so the reciprocal of that would be a 2. And this is going to give me, that would be 2 at the lower limit. Cotangent of pi over 6, well, let's see. Cotangent is cosine over sine. Cosine of pi over 6 is √3 over 2. Sine is 1/2, so it gives you a √3. So that's the second part. All right, now we can also deal with this negative here by switching the limits of integration. That's typically my preferred method of dealing with it. And that will give me the other one first. So now I'm integrating from pi over 3 to pi over 6 because I eliminated the negative. And this is going to give me the natural log of the absolute value of 2 plus √3 minus the natural log of the absolute value, now plugging in pi over 3. The sine of pi over 3 is √3 over 2, so it's 2 over √3. And the cotangent is going to give us 1 over √3. And when we work this out, we can get a common denominator here. This becomes 3 over √3, which of course is just √3. So the way that I would write the final answer, if you want to get it all together, probably for an exact answer, you end up with natural log absolute value of 2 plus √3, which is strictly positive, so you could drop that, minus the natural log of the absolute value of √3. And if you really want to be fancy, you can put those together. They're both natural log. So we get 2 plus √3 over √3. And if you really want to get fancy, you could go ahead and simplify. It is strictly positive. So you get 2 over √3 plus 1. I don't think you could do anything else to simplify that. I think that's about as low as we can go. And this turns out to be a relatively small value. This is about 0.768. So 3/4 of a 1. So looking up here at our graph, on the graph, again, pi over 2 is here, which is about 1.57. So 1 would be maybe this distance out here. So yeah, it's reasonable, right? It's a reasonable approximation. Okay, the next thing we want to talk about is arc length of a curve as a function of y. On occasion, a function is better expressed as a function of y instead of as a function of x. particularly if it has some point where the tangent line goes vertical. So when we're looking at that, we're going to look at something like that. So in that case, all that we require, if the tangent line goes vertical, if we rewrite it as a function of y instead of a function of x, then we can still claim that it's smooth because we basically switched the variables. And then we can take the interval to be the y values from C to D. And then we can say that the arc length formula is essentially the same, except that the function is now a function of y. So this is x as a function of y. So we have g prime of y, which is x. And it goes from the point g of c, again, g of c is the x value, and c is the y value, to the point g of d, d. G of d is the x value, and d is the y value. So it's essentially the same formula. And we're going to look at this one right here. This one is find the arc length of the curve given by x equal 1/3 quantity y squared plus 2 to the 3 halves, which is not a sideways opening parabola, but it is very similar to one. And it looks a lot like a right opening parabola. Now we're interested in the region for y between 0 and 1. So we're looking at this part right here. All right, so y going from y equals 0 to y equal 1. So basically the formula is the same, except that now our function is a function of y instead of as a function of x. And that means that you have to solve the equation for x in terms of y. But it works pretty much the same. I'm going to let you pause the video here, go ahead and work this one out, and turn it back on, and we'll compare our answers. So let's take a look now and see what you got. So this one is a very straightforward one. This is also a very good problem to put on an exam because it's easily doable in the amount of time you would have on an exam. So first we want to start by finding the derivative with respect to y, not x. So we invoke the power rule, bring the 3 halves to the front, reduce the power by 1, which becomes 1/2. Chain rule, remember to take the derivative of the inside function y squared plus 2 to get 2y. Simplifying, we get y equals this times the square root of y squared plus 2. And when we square it, we square the y, so we get y squared. Squaring the radical just flips it off. And then if we distribute, we get y to the 4th plus 2y squared. The step 3 is to add 1 to that. When we add 1, we actually end up with a perfect square trinomial. It does factor as y squared plus 1 quantity squared. That's good because that means that when we put it under the radical in our formula, that we'll be able to take the square root of the perfect square. So coming down here to the second part, that's what we do. We put this under here. When you lift off a radical of something squared, you end up with absolute values. But we have 2 reasons that we can remove them here. First off, y squared plus 1, the smallest value can be is 1, because when you square something, it's always non-negative. So the smallest it could be is 0, which means it's always greater than or equal to 1 for all values of y. Again, that upside down print A stands for the words for all. And then the second reason is because our interval is from y equals 0 to y equal 1. So we know all the y values are positive anyway. And so y squared plus 1 is positive there. Now we go ahead and integrate that. So using the power rule for integration, we get 1/3 y cubed plus y evaluated from 0 to 1. And we get 4/3 as our arc length. And then we always want to do a reasonableness check. So from here to here is a length of 1. This to me does not look like 4/3. It looks closer to 1, but according to our calculations, it is in fact 4/3. It's more than 1. It's 1 1/3. So again, the eye can be deceived whenever our function's curve. The actual length of it is a little bit deceptive. We have one more example I want to work in this particular section, and that is going to be another one where x is written as a function of y. So this time we have x equal 4 times quantity 3 plus y quantity squared, which is a right opening parabola. And we want to know about the section from y equal 1 to y equal 4. Now notice on the x-axis, this is a huge amount right here. We're going out to nearly 200, but the y value goes from 1 to 4, so that's what we're going to integrate over. So go ahead and pause the video, work out the problem, and then turn the video back on and we'll compare answers. This is another tricky one that you probably would never get on an exam because it involves trig substitution and, again, integration by parts with secant cubed, which we've already done. I won't make you go through that again. But we do have trig sub here. So notice when you find g prime, you end up with 8 times the quantity 3 plus y. In this case, it's better not to multiply it out because it's going to lead us to a trig sub. You might not realize that, though, till you get down to the bottom. So you may have to backtrack some. Then we have g prime quantity squared. So we square the 8, we square the parentheses to get this expression, and then we add 1. This, if we multiply it out, is almost certainly not going to refactor as something squared, which is why we need trig substitution. Both terms are positive, so it's going to be tangent. We take the square root of the variable term, and we say 8 times quantity 3 plus y is 1 tangent of theta, 1 because that's a 1. And then, of course, we rebuild what our expression is that's going to go under the radical, which is this 64 times quantity 3 plus y squared plus 1. And this will give us tangent squared of theta plus 1, which is secant squared. So we know that we can replace this part under the radical with secant squared of theta, but that means the differential has to change from dy to d theta. So we come back to our main substitution equation, which is this one, and we solve it for y in terms of theta, and then we take the derivative of both sides with respect to theta. So you can find down here that I took the original substitution equation, I solved it for y and got tangent of theta over 8 minus 3. Taking the derivative with respect to theta, give secant squared of theta over 8, abuse the notation, and swing the d theta around. So this replaces the differential dy. So we get this right here. When we take the square root of secant squared, normally we have to worry about it, but because of the way we defined it in the trig substitution, when it's cosine and secant, it's always strictly positive anyway. We don't have to worry about it. The only one we really have to worry about is tangent squared, because it has different signs in quadrant 4 and quadrant 1, but cosine and secant are both positive. And again, we're defining it in certain quadrants. So when we're looking at this one, we end up with this secant cubed of theta d theta times 1/8. Now, we've already done this one once today, and I said I wouldn't make you do it again. So I gave you the expression right there for how to integrate secant cubed. You get this up here. Now, ours is 1/8 of secant cubed, so we get a 1/8 times each of the 1/2, which gives 1/16. And then we want to evaluate from y equal 1 to y equal 4. We've got to get out of theta and back to y, so we go back to our substitution equation. Sorry, my dog is having a fit. And then we draw the triangle, which you see here. We know tangent of theta is 8 times 3 plus y, so that over adjacent is 1. And that builds the Pythagorean theorem, giving us the hypotenuse. Based on the triangle, then, I know secant of theta has to be this expression, and I already know that tangent theta is this one. And those are the only trig expressions I have. Then I go ahead and substitute those values in place of that expression up here. So tangent of theta gets replaced with this, secant of theta gets replaced with this, and you see these being substituted. Once I've gone back to y, I can drop the y equals from -1 to 4. It does take a little bit of arithmetic and algebra in there to simplify things. I could simplify this further algebraically, but it's already complicated enough. I just went ahead and gave the approximation as about 132. Now let's go back up here to our graph and see if we buy that. So looking at our graph, from here to here is 50. Here to here is 100, and ours is 132-ish. So this from here to here, yeah, okay. It could be 132. I would say anywhere from 125 to 150 is probably reasonable. So this is the last example that I want to work on, finding arc length of a curve. And again, this is in the section on arc length and surface area, which are applications of integration. In the next video, we're going to take a closer look at surface area, which will be a much shorter video.